It's once. It's K. Okay, sorry. Hi, nice to see you again. It's an interesting journey. Actually, we've been working 5 years in a setting which is not completely research, but it's always fun to be here. This is a talk that I've worked with fantastic people. So actually, I've been working in Certora for, in these 5 years with an amazing team, a global team, basically US, Europe, and Israel. And these are the team that helped me make this talk. Shelly was actually helped me start the company, and Chandra was actually helping me here with this work, also building a WebAssembly formal verifier for Certora. John, who actually is originated of many of the core IP in the abstract interpretation, and Yura is actually teaching me about DeFi. So how many of you know DeFi? No, you don't know what DeFi 1. Okay. So DeFi is a cool buzzword. I'm going to show you a little bit. It's a buzzword for decentralized financial application. So you think about it, it's a subset of crypto, but it's kind of interesting things about crypto. Many people hate it. I will tell you a little bit about it today, and also tell you a little bit about how Certora handled it. And everything that I know here is thanks to Yura. Of course, I want to say we have a lot of people that you know from this space. Some of them are your students. Thank you. That help us here. So we are actually learning this space. We are doing a lot of things in abstract interpretation and also SMT solving, and we are interested in hiring. We are a huge group, as you can see. So what I want to talk to you about is 3 things. The first thing is DeFi and Certora. It would be basically understanding a bit what we are facing, and then I want to hint about what do we do for the static analysis. Of course, we have all the abstract domain you're familiar with, but we have a unique pointer analysis for this domain that I want to hint about what it is doing. And finally, because I'm old, I feel like it's a good idea for me to try to, and I'm probably stealing a lot of ideas from Patrick, but I want to somehow try to tell you how I want this field to progress in 40 years. I'm not going to stick around, but I want to actually try to explain how I think, and this is very subjective, of sort of how I think maybe this field can grow. Some of it has to do with the industrial experience in Certora, but some of it is just lessons which I have learned. Okay, so what is DeFi? So this is you can Google probably, you get good information, but this is DeFi in one slide. You think of a financial application that you do in the bank, but it's a financial application which is defined by code. You can define it in the language that we work in, Solidity. Now we're supporting Rust. It doesn't matter. It's a programming language. But the interesting thing in this programming language, you actually define, or maybe not, it's not a programming language, it's more the program. So it actually defines how the financial computation is done, and once it's defined, it's on the blockchain, you cannot change it. Or you can change it, but it's hard to change. So these are programs that actually define financial computation. Some of them are our client, some of them are not. But for example, one example is a stable coin. So what is a stable coin? A stable coin is a coin that emulates a fiat coin. For example, a DAI is a stable coin that emulates the USD. It emulates the dollar. I don't know how many of you know, but actually DAI is actually very used. Where is it used? It's used, for example, in Argentina, because in Argentina, people are not allowed to use dollar, they use DAI. And DAI is actually, there is a sophisticated algorithm that actually implements it and makes sure that it's 1-to-1 to the dollar. And interestingly, if you look, for example, Certora the tool actually found a bug in the core logic of this algorithm. So this algorithm is implemented in code. Oh, I don't know, this is somebody, hopefully this will stop.
Yeah, just have to see.
This, yeah, I've did a lot of mistakes, but I used to be a Windows guy, and now I switched to Apple. Oh, well, let's go down. Okay, so DAI is a stable coin. All of this Go is actually implemented here in London. It's a stable coin. USDC is a very interesting idea. You can think about it as a silly idea. The idea is every time you buy $1, this company goes and buy $1. Okay, so that's a very stable algorithm. Okay, so but funny enough, people found bugs in it too. Okay, so these are stable coins. There are also exchanges. So exchanges actually have sophisticated math, nonlinear math in it. The idea is you have two coins and their multiplication is a constant. From it, you can do something even more general mathematically, which is called AMM. Some of you know from financial things there is market maker. So this automatic market maker. So these are algorithms that automatically trade and decide your benefit. There's lending protocol. Actually, it's Aave. Also the one who compounds. So these are things that you can borrow money, but there is an API in the code that you borrow money. And you can borrow this with cryptocurrency. Of course, you can maybe do it with fiat currency. And liquid staking is probably one of the most interesting things. Also actually, a customer of Certora is Lido. The idea is you can actually define when do you get your benefit. And it's very interesting because people, at least if you see this year, people have got a lot of rewards here. So how is it adapted? So that's an interesting domain. It's and you look at if you are bored from the lecture, you can look into DeFi Llama. DeFi Llama is a website that shows you how much it goes up and down. You need to have a strong heart. So what happened is that you see the currency goes up and down. But the interesting thing is that even in the bear market, it's still actually holding up. Interesting, and it's actually. And you see that actually it's kind of interesting. People are buying, and now since the beginning of the year, it's starting to go up again. So but this is actually one of the most interesting things about this domain for people in abstract interpretation or formal verification. Even though these are very, very small programs, they are very, very tricky. And it's very, very hard to get them right. And what you see here, it's based on a company called Chain Analysis. Unfortunately, they haven't published the one. I wanted to have the one for 2023. It wasn't available at the time of the talk. But what you see here is kind of interesting. You see that, in fact, the number of hacks during the year, they actually get smaller. But they are getting more sophisticated. And people are stealing a lot of money. And the hackers are fantastic people, actually. They know a lot of things, maybe even abstract interpretation. They are, and you see, these are things that, and I'm pretty sure it will be similar. You will check with Chain Analysis, but I'm pretty sure it will be similar in 2023. There were fewer hacks, but each one of them, people are pretty sophisticated. So, of course, I mean, teaching here formal verification makes no sense. So I kind of, this is, of course, Wikipedia looking at formal verification. But I actually want to give you another view of formal verification, which we didn't came, I'm sure, it came from our client. So how many of you know about Johari window? Johari window? Okay, so it seems like I'm teaching you several things. So Johari is actually coming from social science, communication science. It's actually a very nice idea. It's very, very simple conceptually. This is how you give feedback to people. If you are a manager, you have to understand this Johari. So the idea is there is what your employee knows about him and what you know about him. And you need to somehow communicate to him. What are the things that he's doing good and what are your things you're doing bad. So this is actually a client of us explaining how he views Certora, which is lovely. So what he said, this is the protocol, this is the code developer, and this is the hacker. Okay? And basically, this is the bugs that you know, and these are the bugs that other people know. And interestingly, the biggest competitor for Certora, and in fact that's what some of the things that Certora does, these are human auditors. So what are human auditors? These are white hackers, they are very, very smart. They look into your code and they find fantastic things. Okay? And actually Certora team has some people who are doing it actually in a good way without the tool and with the tool. Okay? So hackers usually find bugs here. They are called by these social science people, I hope I'm not, they are calling blind spots, okay? I think Certora, and that's actually what this guy is saying, Ernesto, I don't know if you know him, this Italian guy, he's saying Certora is finding also bugs here. And why is it? Because Certora has, of course, specification, because the tool is comparing to the specification. So we are able to sometimes, actually it's very surprising to us sometimes, when a tool finds a bug, we think it's not real. We go to the customer says, it is real, actually. And some of them, there are bugs that will allow you to completely deplete the code. So we deplete the contract. So we think that this is actually the benefit of formal verification for people, okay? That's Ernesto's idea. So why do we work in this formal verification? So in this domain, one thing which is interesting, this concept which says code is law. So the idea is all the code is open source. By the way, if you want to go to look in all these examples, they're all open. Certora tool is not open source, but you can use a free version of it, or we can get just on the website. But the code is open source, and the code is law. Basically, if you invest in financial system like this, you actually can see the code, and the mathematical definition of it is a law. So that's very interesting. You want to verify the code. The ratio of lines of code for dollars, it's amazing. For me, because all my research is, and I work on very small programs. So this is fantastic. Like you have 50 lines of code with $10 billion. Okay, that's very interesting. Usually it's the opposite. Okay, go to Microsoft. Okay, so the interesting thing, even if the code is not small, is modular. You have this one contract invoking another contract, but you can do some kind of modular analysis to verify that. But still, even though these are small programs, they are very hard to get right. They have a lot of behaviors. They have nonlinear. They have a lot of things. And bugs are really very, very tricky to get. And I'll show you some. But if you look into all the bugs that were found this year, they are fantastic. And interestingly, if you look I remember sort of working with Patrick, he got us to the Airbus project. The code, I remember going to the Airbus team, they say, we never changed the code. This is not the case here. The code is changed frequently, and new versions which are huge, and you have to do it from a business perspective. So you have to come up with a new version all the time. And it's usually not every month, but usually these protocols, at least once a year, they have to come with a new protocol, and it must be more interesting. And so that's actually make it interesting to formally verify. Here you see the maker. I mentioned these are the stable coin. Actually, you use the Certora Prover, and they wrote their own spec. And the Lido team that are now launching the dual governance. It has some game theory in it. Actually, they're using formal verification. Okay, so as I said, it's an interesting domain for formal verification. And it's even interesting for Xavier, I guess. Checking the compiler is very interesting. So this is actually one of the probably favorite bugs this year. It's a protocol called Curve, which implements many, many things, including a stable coin. And it's written in Viper. Viper is a programming language like Python. It doesn't matter. But the interesting thing, you see the Viper compiler has some library to make the code safe. It's called reentrancy. It checks something about providing concurrency. But the interesting thing, the hacker was pretty smart. He understood that there is a bug in the compiler, where actually there is a bug related to how the compiler is mapping the pointers. And he exploited it. I think he stole only 10 million. Okay? Nice guy. So this is an interesting domain. Actually, for us, of course, it wasn't a bad thing because now we have them as a customer. So, and the interesting thing you see, actually, you are mapping the lock is mapped into a different location. So the hacker, which actually knows how to read the source code and the bytecode, the executable code, it knows that in fact you are not locking what you want. And then the exploiter, he actually writes a transaction, sometimes multiple transactions. And then he actually used this to exploit and take the money. So the hacks, even though this is a small code, you may need sometimes several transactions, and they are executed in a rare scenario. You need to be very, very tricky to explore these things. So in this domain, and we had from Kong, there are a lot of tools. So of course, the tools that people usually work in this domain, and these are the most useful tool, is fuzzers. In particular, there is the called Foundry. Foundry is an open source tool which is everybody use for fuzzing. It's very, very useful. It's easy to use. People are using it. The problem with it is that it's hard to find bugs like I show you in the care cases, because these are bugs that involve multiple things. Of course, once you find a bug like this, it is still useful. In fact, we use Foundry when we find a bug. After we find a bug with the tool, we will show it with Foundry because the user is actually understanding how it goes. So we use this tool after we find a bug. But it's hard to use it to prevent bugs. The other approach, of course, here need to be not to introduce a static analysis, either sound or not sound. It doesn't matter. I know here in this domain it's important for us, but I think looking from the perspective of the client, the static analysis is tricky to use because of false alarm, okay? And if you look at it in this domain, people have implemented tools like Slither and others. They implemented best effort tools, but they are actually, yes, Peter?
I mean, from my experience, static analysis is widely used. Fuzzing is very seldom used and very hard to set up. So Francesco?
Plus one what Peter is saying, I think it's false use line.
Yeah, I think
what
he said about the slide is false using.
Yeah,
Okay, fantastic.
I totally disagree with the false positive issue for security, and I can take it offline with the false negative and the use in industry.
Fantastic. Actually, I recommend you. So the good thing about this domain, in this domain there are people from industry, there are people from academia. I recommend to you to listen to Yanis talk. Yanis is a fantastic guy in this domain. He's actually a static analysis. Yanis Samardakis.
Yeah, but he's not working in industry.
It's not.
In industry. He actually came to
Let's. Can we
hardest thing about fuzzing
it's not
is
my
setting it
domain.
up.
I'm not trying to sell you static analysis or so please. I'm not. So the issue is that I think what Francesco is saying is completely right. The issue is that in different domains, people use different things. Okay? In this domain where you have small code, just a second, and it carries a lot of value, people have used static analysis and it's not useful for them a lot, and people have used fuzzing and it is useful for them. There are other domains that I'm not talking about, so I'm not making any claim about Facebook, okay? I'm making a claim about this code. And in this code, people have, by the way, Certora is using static analysis. That's not, so we are using a lot of, okay, I want to continue, please. Thank you. Okay, so yeah, good. I might do, okay. I need to go on time. I want to go to the juice, actually. Okay, so the third thing that people use, bounded model checking or tools like Daphne and others, actually Certora is similar in many respects. It's basically use what's called deductive verification. You take the code, you reduce it to a formula. This is great, but it's computationally expensive. And of course, in this domain, people use, and if people have used successfully tools like Core, K, Lean. This is also interesting, especially because you can get some code to be right, and it's but it requires a lot of effort. And I think, at least from what we see in our client, it's very hard. So maybe that's, and I'm sorry I don't have all the tools here, but I'm just trying to explain what happened in this domain. It's very, very only for this crypto domain. So on the left hand, you see all these very, very powerful tools. And on the right-hand side, you see tools which are easy to use. And here I'm using both static analysis and fuzzers, so they're all together. They're more easy to use because they don't require specification. We are trying to build something in the middle. We are trying to build something which is maybe not as powerful as Quark. I know now I have to use another name, but I forgot. But it is actually, it's running on the executable code. We are trying to make the tool easy to use, and we are trying to make the tool without false alarm, and you can check it. We are modular, but unlike tools like Daphne or Vipers, we're not requiring pre and post condition for every procedure. We're trying to be, and actually there we have Jochen from Andreas, thank you. So we are trying to make it so we can scale it up. And there's a white paper, you can read about it. So how does it work? We basically have the technology, which is the Certora Prover, which involves static analysis and abstract interpretation and SMT solving. And we also have something I'm not going to be able to talk about, but we have mutation testing to check the spec, because part of the bugs that we have are actually in the spec themselves. So we are trying to check them. And we have a language that you can define whole triples, but you can also define relational properties. So we have a spec language, and this is open. You can use for writing the specifications. So how does it work? I mean, it's not any use for any of you. You have this invariant, you have this property that you want, you have the code, then you feed it to the Certora Prover, and you get a proof, and you get a bug. And the bug is actually indicating some kind of what we call counterexample to induction. You are starting from a state that satisfies the invariant into a state that violates the invariant. Of course, it's not the truth, because the SMT solver or even the static analysis can time out when you have a complex code, and it is the case for us. It is the case for us. We have problem with the static analysis, we have problem with the SMT. So in practice, it's actually pretty much more sophisticated. Here I'm showing you the tool chain for EVM. We have something similar for WebAssembly. So we start from the Solidity, we take the compiler, we take the EVM. This is interesting, actually. We decompile the code into high level. It's called TAP. It's our own internal representation where we handle many things. This we are implementing actually abstract interpretation here. So basically we have this tool, and that's what I'm going to show about trust by verify. We have abstract interpretation of low-level memory. And actually you see that one of the benefits of this tool, because it enforces stronger of invariant of the code, we are finding bugs in the compiler itself. So we are not formally verifying. The compiler is more like translation validation. We are checking properties of it using abstract interpretation. And of course, this is actually where we have a lot of IP, but I'm not going to talk about it. It's more Yaroslav's work in the SMT team here actually in Europe. Darion, we are actually doing a lot of things to make the SMT solver, and of course thanks to Nicola and others, to make the SMT solver work. Where this tool is very, very useful is where you have, basically you are changing your code. You have a bug after exploit or something, or you have a new version of the code, and you want to check that the invariant are still maintained. So it actually goes into your code and you check it. So maybe this is just show you a simple example. This is a trivial bug. You see you have invariant here. And you see that the tool actually found that if you are doing, this is a very, very rare corner case, that you are transferring the money to yourself. And then, in fact, if you're transferring the money to yourself, you can earn money. And the way tool is, and actually this is a bug that can happen even in normal banks, by the way. So, and the way the tool checks it, because there is the invariant, it checks the invariant. Interestingly, you see when you fix the code, for example, here you make the code more functional, we cannot show you that you have no bugs, but at least we can show you that these invariants are maintained. Okay, so second part of the talk. I want to talk to you about what we do in Certora. We do many things, but one of the things we do abstract interpretation. We take state-of-the-art abstract interpreter, but we actually have to do some more things. So what is the motivation? We are allowing the programmer to write the spec in a very high level language. Think of whole triple, or you think of even simple pre and post condition. But the code itself is written in very low level. In fact, we only see the bytecode. And this is the design decision we made. People say we made a mistake. We ask the VC, they say you should have your own programming language. But we are not that ambitious. Okay? So we tackle the low level code. And the interesting thing, the low-level code has all the nightmares that you have in the world. Non-linear and all of these things, and storage. And I know you guys, if you come from USMT, you think you want to use a rate here, good luck. So we know that a lot of things are hard here. And we have no type information, and the control and data interfere. So this is where we have to do things here. And the way we do is we cheat, but we check it. We basically have some assumption about the invariant, and we enforce them. So maybe just a very, very simple example. It's not a realistic one. So this is just a contract in Solidity. But if you don't know Solidity, I don't care. Just think about it. You have arrays, or you have nested arrays, and you have dynamic arrays. So in fact, here Logosov should be happy. He has a solution, he will tell you. Okay? Do you think this solution will work, Logosov? It doesn't. So the answer is no way. Okay? This solution is great for these kind of programs. Okay? But let's see the program that we have. So this is the program that the compiler generates. Okay? And I know I'm not going to go, but you see here. And actually, if you think about Solidity, you go in WebAssembly, it's the same. You see that everything is storage, and actually everything, there is a double in direction of the storage. So you need to do reasoning here. And proving this assertion, you cannot use the Logosov algorithm or ours, it doesn't matter, wherever you want. You need to recover the low-level ones. So what do? We also do some kind of commutative diagram of the abstract interpreter. And so basically, in the case of the Logosov, this is working here, okay? What we do, we implement something that actually works on the low-level code. So here you see that we have actually reason about all these bit manipulation, storage, what you read. And what we do from that, we recover something which is called middle level. And the middle level, you see, actually, it's almost like the same. It doesn't have the names, but it has the structural equivalence about the code. And then we can apply the Logosov or others, it doesn't matter. But the idea is you have to recover this. Okay? So this is the idea. Of course, you have to reason about what the compiler is doing. And the compiler is doing many things, which is common, actually. So, for example, memory allocation is not using malloc. It's using the concept called bump allocation. So basically, every time you allocate memory, you see now there's the storage, it's allocate the memory, it's read, so now you see this piece of memory is allocated. By the way, I'm simplifying things. The allocation need not be continuous, but I'm making my life easier. The compiler actually can deal with things, but it's not continuous. But this is actually getting here. Now we are writing into storage, and it's actually, now it's initialized. So we remember the initialization. So essentially, we can recover how the memory is doing. And now you see there's another allocation. So it's still allocated. Oops. Okay, and then it must be initialized. So this is how it goes. In practice, it's way more complex. I won't be able to explain, but it's combined data flow and control flow. It's associate basically things like SSA. It associates the static location with things. It checks several things that, in fact, the compiler doesn't think about. For example, memory safety is something that let us prove all these assertions. So we're actually checking these things. You see here, people are tweeting about it. That's nice. So people are tweeting about it, that we have a tool for automatically detecting bugs in the compiler. That's not the case, because this is not our intention. But still, you see that we are detecting bugs in the compiler, and we are actually getting acknowledgement and bug bounty for finding bugs in the compiler with the static analysis. But the idea is the static analysis enforcing this invariant and checking them. Okay. So now I'm the last part of the talk, but the most tricky. How am I doing in time? Okay, so now I have to sort of tell you what I think, and that's, again, very, very subjective. So how will it be in the next 40 years? I said, I don't know. So this is, of course, I think Patrick has done a good work here, and you guys, we just heard from Jens. We can connect with many, many fields. And abstract interpretation could be thought of in a concept that you can use to explain many things. So Peter in his group with separation logic, with program logic. Maybe you can think of database theory, logic, decision procedure. We work with algorithms, machine learning, cryptography. It's actually interesting programming language. With Sharon, we work in learning theory. type theory, and I'm sure I've not mentioned all of them. There are a lot of things that you can connect abstract interpretations. That's the beauty of it. And I think it's great. You can find more here, I'm sure. But this is wonderful. Wish 2 is actually very interesting. That's a mistake I've done many times, and I've seen it also others doing. So how many of you know Vivek Sarkar? A few of you. So Vivek is actually, I have never worked with him, but he's kind of managed Eran Yav, which was my student, and he's telling me that I'm doing something completely wrong, and he's probably right. And so as a researcher, and so this is kind of trying to understand from a Vivek's perspective, I'm stealing a slide, sorry, how the world is looking in programming. So these are the expert programmers, okay? These are hackers, people who are really care about these small programs implementing some very, very tricky algorithms. Okay? These are the programmers, and maybe Facebook, maybe they are, these are the end users. Where do you think Certora is, and actually my research is? Do you want to guess? Exactly. Certora, we are here. It's interesting that we are making good money here, but it's a small domain. These are very, very small people. Actually, these are small, but you need to understand actually where you are, and I think there are different challenges. I think all of them are challenging. They are nothing bad, but I've seen people that are here and they're claiming they're here, and that's not good. Okay? I think you want to know, and even you, it's something you have to be conscious about. Which people are you helping? And I think we need to understand if maybe there are other domains. So I think this is Vivek's point. I think it's a good point. Okay. The other thing I learned probably from Patrick, but also from my own experiences, that less is more. That specialization is the key. Often I've seen people, including my students, say, I have this algorithm that solves everything. Usually it means it solves nothing. Okay? So what we need to know, we need to somehow understand what do we do and make certain assumptions about the domain. In Certora, every day we have this nonlinear equation with exponent, whatever, and then we show it to Jochen and you say, no, you really implement that. So we need to understand what we are doing, and I think making some assumption about nonlinear arithmetic and bounded storage, what we did in the shape analysis, untyped languages, and I've seen it in our domain. There are people that say, oh, and I don't want to use name, they use a new programming language and say they eliminate all the logical mistakes. Good luck. Okay? Whether it's a kernel or whatever, you're not going to eliminate logical mistakes with programming language. Programming language are great, but mistakes in logic people do in all programming languages, probably in Haskell too. Okay? So we need to have some kind of understanding of something of things. Even untyped languages, they are not so bad. We are working in untyped language, and people are moving the program to typed language, and they are introducing more bugs. Okay? So untyped languages, they have some problems, but we need to understand at the end of the day, people care about correctness. Okay? And correctness doesn't mean type safety, I'm sorry. Okay? It means correctness, it means it implements what it does. Okay? And so part of the point to say what it does. Liveness is actually something that in the beginning of my career I've ignored, but one of the things I learned in Certora that actually liveness is very interesting. When we ask our clients what they care about, they usually care about liveness. The most interesting properties about DeFi is what's called solvency. I deposit the money, I want to be able to eventually withdraw it. Okay, and most of the bugs, the interesting bugs that Certora finds, or human finds, they are solvency issues. Okay? We don't even know how to specify it, but that's a separate issue. But these are things that you need to know, liveness properties. But if you are caring about CTL, LTL, it's not the issue. You need to understand what they care about in terms of the property, and you need to think about the code, what they are worried from, what is the attack vector. Also data structure, we work in the work of shape analysis, but I think we call, and I think Hongso later, and the separation logic people, they have done more, but I think we need to understand what classes of data structure people care about. For example, in crypto, we have Merkle tree, we have all of these things, and we're having a hard time about it. So we have a lot of tricky data structure to reason about it, and we hope people will come with abstract interpretation to solve them. And in the area of distributed system, people are looking into consensus, but there are a lot of things which are interesting about distributed system, and maybe we can tackle them. And again, the key idea is specialization. Even working in a abstract interpretation, maybe I will say something completely politically incorrect. Abstract interpretation that takes as a single program is interesting, okay? If it's an interesting program, okay? And I think this is something to, at least it's my own opinion. Another thing which is probably questionable, and take it with some grain of salt, but this is my own opinion, and I think I've kind of been almost consistent here, maybe especially in the last 10 years, is to understand that actually automatic program analysis, so sort of maybe this is how I should have answered Logos's question, but automatic program analysis is very limited. The issue is that if the user is not involved in the game, it's very, very tricky to get results. So memory safety, of course, is a good idea, but the idea is you need the program to be, especially if you're looking for logical errors, you need the programmer to tell you what it's supposed to do. And assertion is one way. We use also relay guarantee in Certora. Abstraction, we can even say, and actually maybe something that you don't think it's true, at least in our domain, people are pretty sophisticated. Our users, they understand it, we can explain them a concept like a join. So we can actually have them in the loop. It's not so bad. People are trying to optimize, to automate everything. But I think like Knut mentioned, sometimes actually having people understanding things, even things like widening and narrowing, it has this appeal, and if you can explain to a programmer, they can use it. And maybe another thing that is actually in Certora is a big thing for us, and maybe you don't think it's an issue. Failure diagnosis. When our tool finds a bug, it will sometimes take us a lot of time understanding what is the bug, or even if it's a timeout or whatever, it's even harder. Understanding what is it that's making the problem hard, and maybe extracting something from the code. So I think I encourage you to think of some kind of, maybe it's related to what Xavier was saying. Maybe even something like abstraction. Have the user, have the programmer involved how the abstraction is being done. The last one, probably I think I'm sure everybody here agree, we need to have more impact of this domain. I think we are a fantastic team, but I think if I compare to other domains that we work with, and I think we can have more impact. Of course, the fact that we have industry, but I don't think only in the industry, like works like Antoine Mounet that basically have open source tools that people can use, have more industrial application, find a killer application, like I mentioned already, DeFi, but maybe privacy, maybe other domains, and maybe also doing things that other domains are doing, for example, computer network, doing some public good, doing something that people care about. And maybe also find, and I think that's actually something that other domains, for example, I'm in Israel, and Israel there's a very huge, a good, strong cryptographic community. And one of the things which is lovely there, and sometimes Adi Shamir will come and say, these are the 10 open problems, okay? And then we stick on it, and nobody, so we need to have a form, and maybe this is the form, but we need to have a form that we share. And actually one of the things which is lovely about crypto, I know many people hate crypto, people share. All our clients we got it from competitors, so it's great. People share. Sharing is actually make you work better. And I think we can share open problems together to make this field more progress. Maybe Absinthe will tell us what are the things they're struggling with, and we tell you what are the things that we are struggling with. And we find ways to share. I think this is it. I just want to close with these things. I've seen it too many times, but still I want to tell you some myths about this field. So if we look into at least competitors, even coming, they always say that formal verification is something to find proofs. But I think at least for us in Certora and many other domains, the customer really wants to, they want to, from a marketing perspective, it is the case. They have, if you look into the website, they will say it's formally verified. They don't say what, and they formally verified with Certora. And then they find a bargain. So the issue is that the biggest value of formal verification probably for software and for hardware is bugs. Of course, we saw in many things that the hardest problem is computational, but it is true probably, but for us in Certora, getting the spec right is very hard, and if you want to help us, please approach us. Writing the spec for something interesting is very, very hard, and getting the spec right, we have tools now, we're also using Core and SAT and other methods, but getting the spec right is very hard for us and for our client. Formal verification, of course, doesn't produce a bulletproof code, not because of the soundness of the tool. Our tool has certain soundness issues, but I think it's more like the spec. The biggest problem is the spec. I can show you that many times we prove specs and client prove specs and it turns to be tautology or something. So the biggest problem is the spec. But even formal verification, we don't, if you look into many of the bugs that people have found in the DeFi, some of them is price manipulation attack. And price manipulation attack, you look it up, it's very, very hard to formalize mathematically. It's the idea that you do something and there's incentive and then somebody incentivizes you to do something. So there are some things that are actually very hard to find with formal verification. So we are not producing bulletproof code, but I think, and this is something that we cannot quantify now because we have a very small domain, but we really believe that our code that's used by us is more secure. And one way that you can quantify, you see that people like to steal it more. Okay? People say, this is formally verified with Certora, let's use it, because it's considered to be more safe. So it is actually, and it's a small domain, we have not been around, but we think that, and people, for example, they use bug bounties, we also now plan to use bug bounties. So basically, let the community, in this domain actually, bug bounties are huge. Look at it out, look at it. So we plan to give bug bounties for people to find bugs in customers that we work with. In order, and they can find bugs in our code, in the code of the client, of course, or even bugs in the spec, which is fine. Other thing I think I mentioned, the competitor for this is basic code review or manual editing, and some people will say it's formally verified, and then it's not need to be audited, or not to need to be tested, it's need to be tested and audited. It's improved the auditing, and we have some auditors. I don't know if you know this platform called Code Arena. So Code Arena is a platform for community audit, and these people are using our tool, that's great. So it's a lot of people, and they're writing spec, and they're using the tool in the audit. And they, of course, get reward either from the protocol or from us. The last thing is that formal verification, people say that you do it after you finish testing and all the other things. We want to have something like shift left where people write the specification first. This is my hope. Not yet achieved, but hope. Thank you very much. This is sort of the takeaway just from the talk. Bug finding is hard. We use abstract interpretation SMT together. So we do static analysis, and they help each other. So static analysis help the SMT in the complexity, and SMT help the static analysis because we have no false alarm. We give you a program. So that's the idea. And we prove the correctness of the code starting from an arbitrary state, unlike fuzzing. Thank you. Questions?
I have a question. When you spoke about the analysis of object code, do you know the source?
So the answer is, do we know the source? So
Yeah.
yes, the answer is we know the source, but we are not using the source. We are
Okay, because there was work by Xavier Rival, and the idea is that if you know the analysis of the code, if you know how it is translated, in principle, you are able to build the analysis of the object code and check it.
I know. This was part of his PhD. Remember that I was in the loop.
But he had no success.
No. So that's it. So that's.
And let me finish. And this is because of the community, which was saying, what you do is stupid. Just take a proof compiler, and you don't need any of your techniques. So there is also a problem in what you showed is what people understand and what they are ready to accept. And unfortunately, in your first picture with abstract interpretation in the middle, if you are in the middle, it's a nice picture. But if you are outside, you understand nothing what is in the middle. And so I think education is missing in your list of wishes.
Okay, so education definitely is missing. Another thing, to answer your thing about verifying the compiler, I think it's more like a question, but it's very, very hard to verify compilers. Like I think people have, another thing I should say, modesty is very, very important for our community. and I am suffering from that. Yeah, I suffer a lot from this. Modesty is very important for us. Verifying a compiler like Solidity, the attempt is very, very hard. The thing, and also maybe I didn't say, we are Certora. We want to do something and stay alive, and we have a small budget, and we have customers that are paying us. So we need to tell, if we tell them that they need to wait until a verified compiler, that's not an answer they want. They come to us either as audit to check their code, or they are subscription to our service and they write the spec. So we need to make sure that we cannot dictate a programming language. And in fact, even we have worked with the Solidity team, and they say all the time, you look into the website, the Ethereum, that they are producing this data for Certora, and you ask them when, they say June 2026, whatever. So, okay, so we are more pragmatic. It's not a research problem, I apologize. But I think even from a research, it's not so easy to, and I think going back to Xavier's work, which I actually seems to know, this actually, I have to be careful here, but it didn't take into account the properties of the code that we are doing. We are looking into this code, and actually we do have failures. Sometimes we run the analysis, and the customer is implementing something that, for example, violates memory safety, and this is intentional. People are using and that's that our tool will fail, and so we are, and then we do something. We have to do something specialized.
May I ask you another question? I remember an evaluation in my team in INRIA a few years ago, and the evaluator says, "Can you explain why abstract interpretation is a failure?" So I said that's too hard a problem, but maybe you have some ideas.
So why is I'm not sure I understood the question. The question is
Failure instance that it's very located to few people and does not expand beyond a little circle of specialists.
No. So we see here that we have a community growing of abstract interpretation. I can tell you that, for example, in my research, we work with Jorge and with Ari Gurfinkel. We work with the Linux team, and the Linux team actually really like abstract interpretation. So we are saying, I think we have a complex theory. I don't know about you, but I'm not you could see I'm not the best educator in the world. So getting these things take time, and we can be better. Even in Certora, if you ask people, we usually ask our programmer what they want, and we think that they want us to solve timeout or whatever. They say, oh, give a decent documentation. We say, this we don't know. So we need to find ways to make our material more accessible. If you compare, for example, to other domains, I don't know, learning theory is a very, very interesting topic, but Valiant found very interesting way to find it. So we need to find ways to communicate. I think there is impact of abstract interpretation. The fact that the Berkeley packet filter is doing abstract interpretation, if the join is right or not right, it doesn't matter, but people understand that abstract interpretation is useful. And we understand in Certora, when I remember when we implemented the first tool, we kind of did something like Daphne or others. We did a poor man's version, and actually it was very useful to find a bug because the code was very simple. But what happened is that once the code gets very complex, we are running after the complex code. So in fact, we are seeing, and even our customers are seeing the value of abstract interpretation.
All right, unless we have a pressing question, I think.
I just wanted
Okay.
to answer to Mooly, I think. Oh, it was just for your example on the array analysis. To be exact, the paper was on abstract domain, or better, a functor abstract domain. So that was not implementation. If you go in the final section of the paper, the implementation of MSIL, which is at the bytecode level. So we analyze unstructured code. Probably easier than the one you analyzed, but that was not all the analysis.
Yeah, but the bytecode that you had is bytecode of Java or something like that, or C#. That's not the bytecode here.
Yeah, exactly, but never say that.
Okay, let's thank Mooly again.